For millennia, we have explained the existence of the stars and the oceans through creation myths, stories designed to place humanity at the center of a purposeful beginning. Modern astrophysics reveals a much more counterintuitive reality. Everything we can see, the galaxies, the planets, and the water we drink, represents a tiny fraction of the cosmos. The visible world is a statistical outlier. This breakdown shows the energy and matter that comprise our universe. Normal matter, the atoms that build stars, oceans, and human beings, accounts for only 5% of the total. The remaining 95% consists of substances we cannot directly see or measure, dark matter and dark energy. Understanding our own origin story requires tracing the history of this invisible majority. The world we experience exists within the constraints of these hidden forces, the architects that built our home, and the energy determining its destiny. Immediately after the Big Bang, the universe was a featureless expanse of hot gas. There were no stars and no organized structures, only a nearly uniform distribution of matter. While visible gas remained dispersed, dark matter particles moved slowly enough to respond to gravity. These unseen particles began to gradually clump together, forming the first dense pockets of mass in the early universe. Through hierarchical structure formation, these small clumps merged over eons. Low-mass dark matter halos formed first, and they eventually coalesced into the massive gravitational wells required to host entire galaxies. This simulation reveals the resulting large-scale structure, a colossal web-like scaffolding of dark matter filaments that stretches across the entire observable universe. The bright orange nodes at the intersections represent areas of immense gravitational pull. These nodes acted as gravitational sinks, drawing in the surrounding gas and dust. Once trapped inside a dark matter halo, gas became dense enough to ignite the first stars and form spiral structures of galaxies like Andromeda. Without this invisible scaffolding to act as an anchor, the gas required to build the Milky Way would have remained scattered, preventing the formation of our Sun and the planets orbiting it. Within our own solar system, the early Earth began as a molten, hostile rock. Its surface temperatures were so high that liquid water was physically impossible to maintain. If the planet was too hot to hold water during its birth, we are left with a central mystery. How did the Earth acquire its massive oceans? Scientists solve this by measuring the ratio of deuterium, a heavier isotope, to standard hydrogen. Because this ratio is set during a body's formation, comparing Earth's seawater against various icy bodies identifies which objects contributed to our water inventory. Measurements from comets like 67P show deuterium levels significantly higher than Earth's oceans, indicating comets likely provided less than 10% of our water. The data reveals a different match: carbonaceous chondrites. These are icy planetesimals originating from the asteroid belt, whose isotopic signatures align precisely with the water on Earth today. During the chaotic early history of our solar system, gravitational shifts sent these icy asteroids on a collision course with Earth. Over millions of years, these impacts delivered the water that would eventually fill our ocean basins. The water necessary for life was a late addition to our world, delivered by a bombardment of ancient debris that survived the formation of our solar system. Because dark matter's gravity successfully built the structured universe we see, cosmologists long assumed that the expansion of space would eventually slow down. In 1998, observations of distant exploding stars, like the faint supernova seen in this Hubble image, disproved that assumption. Data from these supernovas showed that distant galaxies are moving away from us at an increasing rate. The expansion of the universe is accelerating. This acceleration is driven by dark energy, a mysterious force that makes up 70%